たいと思います。どうもお集まりいただきありがとうございます。いろんなところにいろんな形で公募したので、どういう方が来られているのか私も全く把握していないんですけども、東大の中の方ってどれくらいいます？いないの1人。これか。あとは外からですね。話してくれる方は急に来ることが決まって1ヶ月前ぐらいから連絡をもらってたんですけれども、いつ来るかっていうのがちょっとよく分かんなくて、アナウンスかけられるほど余裕のある時期に場所を決められなかったので、急遽ここを取ってやることにしたんですけれども、Google で研究者をやっている人です。分散ストレージシステムが専門で、ここ何年ぐらいですか？
This project, maybe 2 years.
もう数年間その分散ストレージシステムの研究をやって、それで、去年だったかユーズニックス NCC で発表したフラッシュと、ハードディスクの間の分散ストレージシステムでフラッシュをキャッシュに置いて下にハードディスクを置いてっていうような構造でなるべく IOPS であるとかスループトであるとかそういったものを上げようという構造を取ったときに、フラッシュシステム、フラッシュの部分にどれぐらいの容量を割り当てればいいかという最適化をしましたという論文を彼らの研究グループが出しているんですけれども、それのちょっと詳しい話を少し長めに時間を取って、いい機会なのでやっていただこうと、そういった趣旨の内容でございます。で時間は結構たくさん取ってありますので、彼にもなるべくゆっくり話してもらうようにしますので、もしわからないところ等あれば、気軽に止めてもらってもいいですし、質問していただければと思います。
Okay, great. Thank you, Sato-san, for organizing everything here. This is a 30-minute talk, so we have plenty of time. So if I'm going too fast, please interrupt me. Or if you don't understand something, I'm sure Sato-san can help translate things into Japanese. There's a number of things that I think are interesting about this work that might be relevant for people studying computer science or working in this field in general. What I'm about to describe is basically a feature of Google's Colossus file system. So the Google GFS paper about the Google file system came out about 10 years ago now. And so obviously there's been a lot of continual development of literally hundreds of engineers working on successor systems to store data in Google data centers. And this is about one feature in particular about how to best utilize flash devices in a large-scale distributed file system. So this is my research group at Google. So I'm the manager, and Christoph and Arif are two of my closest collaborators. And we have been working for the last 5 years in a team called Storage Analytics, which uses statistics and operations research and math to help improve the design of distributed systems at Google. So this is the general overview of my talk. I'm going to talk a little bit about the motivation of this work. I'm going to describe the system we call Janus, which is a feature of Colossus, our file system. I'll talk about the optimization formulation. Then I'll show some evaluation from Google data centers. And then I'll recap what we learned from this project. So, if you haven't seen a modern data center, this is a picture of one of the Google data centers inside. So these are, really massive warehouse facilities, which are typically located in places with cheap power and cheap real estate. So I don't think that includes downtown Tokyo, but it usually includes rural areas of America or Europe. We do have data centers in Taiwan, and I'm not as familiar with the Asian data centers, but I know there's some in Taiwan. And most recently, both Google as well as our competitors, Facebook and Microsoft, have started moving very far north for very cold environments so that we get natural cooling of the computers. One of the largest the cost of running these data centers is just cooling them all down. So one of Google's newest data centers is in Finland, in the Gulf of Finland there, and it pumps in very cold seawater to naturally cool all of the servers. And similarly, Microsoft and Facebook have explored data centers in places like Iceland or other places where electricity is cheap or and the air is cool. But I'm not mostly talking about power for this talk. I'm talking about disk drives. So you can imagine for a facility this large, these are racks of computers, and there's 1 U racks there, and each one of those has a number of disk drives in it. So you're looking at many, many disk drives right there. This could be hundreds of thousands of disk drives, for example, connected to tens of thousands of servers. And so there's the question is, well, what happens as disk drive sizes get larger and larger? So it takes, for the commodity class of disk drives that Google purchases, the very cheap ones, you get maybe a 2 gig or a 3 gig or a 4 gig disk drive, and you just have one spindle with it. You can do the same number of random seek operations to a 2 gigabyte drive as you can to a 4 gigabyte drive. So in each case, it takes approximately 15 milliseconds, maybe 10 to 15 milliseconds to seek, for the disk head to seek to different parts of the disk. That's kind of technical. Does everybody follow what I'm talking about with the disk head? Is that clear? Okay. Just wanted to make sure. And but as the disk drives get larger and larger, the IOP capacity doesn't increase much. So this represents hard disk drives. And so I removed the labels for confidentiality, but you can imagine 2 gigabyte disk drives, 4 gigabyte disk drives, upcoming 6 gigabyte and larger disk drives. You can still do the same number of I/O operations per second, approximately. It's still at a very low number, and it's not getting faster. Whereas with flash, you store a lot less capacity, but the number of I/O operations per second that you can do is much higher. So what this means is, as your data center moves from being filled with 2 gigabyte disk drives to being filled with 6 gigabyte disk drives, suddenly the number of I/O operations per second that you can do per gigabyte, per terabyte of data that you store decreases dramatically. So disk drives are becoming suitable only for colder and colder archival data that is not read very often. So this is why it's imperative that we start putting the hottest data on flash. And there's many ways to do this in many different types of applications. If you have a MySQL database, thank you. I can be lazy on this, it's good. If you have a MySQL database, there will be caching technologies. You can, memcache or something. You can do key value stores, and you can put your hottest data on flash. But that differs, by each application. You need to tune it carefully and maybe turn up some extra software and figure out how to cache that data. If you're running a large, data center with lots of different engineers and external customers running their own software there, we wanted to have a system at the file system level that identifies the hot data and automatically caches it, so that we don't have to rely on the user being sophisticated enough to turn up memcache or find some other type of caching system to put data on flash. In a typical Google data center, there'll be thousands of users and applications. There'll be web search jobs that are crawling the internet, converting, extracting text from content. In the case of Japanese, doing word segmentation so that we can find the spaces between the words. Serving up ads, serving email, video processing, transcoding from different video codecs to other video codecs. All of these different jobs, are working on separate data sets, and sometimes they're reading really, really hot data, and sometimes they're reading really, really cold data. So many jobs, the mean age of the data, of the bytes that they read, we find are less than a minute old. And many older jobs are primarily working on data that's 30 days or older. So for all these types of jobs back here, these are applications that are reading really old data, and they're probably going to be fine with disk drives. But all of these jobs down here that are reading really, really hot data, that data should be on flash. But there's 5,000 different jobs. Maybe 1 or 2 of these are MySQL, or maybe 2 or 3 others are some other type of system. So we really want to catch all caching technology at the file system level and not rely on each of those 5,000 jobs being reconfigured to manually place their data on Flash. We want something automatic and in the background. So the way we came up with doing this was by provisioning and allocating Flash based on historical workload analysis. So we take sampled RPC traces. So I'm in the context of a distributed file system like this, I'm talking about a system which may have tens of thousands of servers, chunk servers we call them, with local disk drives, and then some coordination processes that know which server has which data. So you have a single file system namespace, but maybe 10,000 servers. And so there's far too much data to analyze everything, but we can sample RPCs, the individual read and write RPCs, for example. And then we want to do the optimization of Flash allocation between those workloads so that we can say, okay, these files are being read very frequently after they're written, and these files in this directory over here are typically not read at all for the first month that they're around. So let's put those directly on disk drives. And then we want to use that historical analysis to inform real-time placement and offline provisioning. And I'll get into a little more detail about what I mean with that. Before I do that, I should talk about some of the related work in this space. So some of these ideas are not new, some are more new. In general, people have been doing multi-tiered storage system for memory, solid-state disk, and tape for at least 20 years or so. A big difference from what I'm talking about and some of that earlier work is that this is a distributed cloud-scale environment. So most of that work took place with single large file servers or enterprise appliances. Whereas at the data center context, if you have 100,000 different servers, you have many different challenges in terms of keeping track of the workloads and the access patterns. It's more federated. There are many early studies from Sprite and BSD that characterize user activity, access patterns, and file lifetimes for caching strategies. These studies were very useful and were done mostly for the context of things like the buffer cache and understanding the optimal read-ahead strategies inside the kernel of a single operating system on a single machine. Also, Blaze was a Linux project for monitoring remote procedure calls. Again, one of the big differences here is taking some of those ideas and massively scaling them to a distributed environment where no single host has a full global view of the actual activity and access patterns, because some of those requests are going to different computers. And so it becomes a fundamentally different problem in that case. Caching, of course, there's many great papers on caching technologies. LRU and FIFO would be the two most common, but there's also many approximations of those, such as second chance, which are sometimes easier to implement in practice, but give you almost as good a performance as LRU. So for the work I'm describing here, we are inserting new files that we believe to be hot into the cache at write time, and we're expiring them from the cache using an approximation of FIFO. I also have some results from LRU, which is better, as you might expect, but is a little bit more challenging in this distributed environment for reasons I'll also describe. There's also been some economic studies of enterprise workloads for replacing disk with flash storage. So I think on the next slide, I'll show you a finding from a paper in that area 5 years ago and what we see today, which I think highlights how the economics of flash have changed dramatically for data centers. And this is in large part due to the proliferation of flash devices in consumer electronics, lowering the cost of flash for other users as well. So the first question is simply, if you're a large customer like Google that you might have, is replacing disk with flash cost effective? That's unknown. That was unknown to us a couple of years ago. As I mentioned earlier, the data on disk is limited by the number of I/O operations per second that you can issue to those disk drives. And flash has essentially, by comparison, unlimited I/O operations. Many orders of magnitude more random I/O operations per second can you issue to flash. So at least for us, we're nowhere near pushing the best flash hardware to its full potential in that dimension. As of January of last year, when I first put these slides together, we got about 1.5 IOPS on disk per dollar, and about 1 gigabyte of flash per dollar. And this lets us calculate sort of a break-even point, which is to say that all data in flash is cost-effective if a workload has more than 60 IOPS per gigabyte. So if for every gigabyte of data you store, if you have to access randomly within that gigabyte 60 times a second, if you need to access it that much or more, flash is probably cheaper because you're going to have to buy mini disk drives with enough spindles to do 60 IOPS per gigabyte otherwise, and you'll have wasted space. So that was the break-even point in 2008, and that was reported by some Microsoft researchers in this paper. But we find something very different today. The green dots represent workloads at Google, so these are different jobs. You know, one of these might be Gmail users in Europe, one of these might be the web search crawler in North America, but they're just different users and jobs, and each one of them has two dimensions: the number of bytes that are stored by that user and the number of I/O operations per second for that user. So you see things like, this dot here is pretty cold. This is 10 terabytes of data that is accessed, with 20 IOPS or something. So it's pretty cold. So it doesn't make sense to put that on flash. That should stay on disk. But then all of these up here are getting pretty hot, where you've got, 1 terabyte of data and over 10,000 I/O operations per second. So that almost made sense to put that entirely in flash, even in 2008. But it definitely makes sense to put it in 2013. So these lines are scaled based on the price drop of flash hardware versus the relative price stability of disk drives. So both have dropped, but flash has dropped significantly faster. So we now have all of these workloads where it makes sense to put them entirely in flash. And furthermore, if we can segment these workloads further, we can split them apart to parts that are more cacheable, and those that are hotter and those that are colder. For example, this dot here, suppose this dot is all Gmail messages in Japan, all Gmail files in Japan. If we could further segregate that to put the hot users that read their email frequently and the cold users, we could turn that into 2 dots, and we could put the hotter dot in flash. So the point is simply, if you can segregate your workloads to find the hottest ones, it makes cost-effective sense to put that data on flash. We can save millions of dollars for the company to put data on flash if we find the right workloads. So how do we do that? How do you use flash in a large distributed file system? The usual approach is to insert to flash on the first read. But this can be expensive with distributed disk and flash. Instead, our approach is to insert to the flash on write time. A huge fraction of the read operations go to the very youngest data. So if we insert on write and we have no reentry into flash after eviction with something like FIFO. We have 2 options though for eviction. We have LRU, least recently used, where this has a high bookkeeping and communication cost in distributed file systems. To give you an example of why that's the case, suppose you're storing distributed file systems like I'm talking about typically store the data either replicated or read Sullivan encoded. In either case, you store a file in this file system. In the replicated case, identical copies of that file will be on 3 different computers. In the read Sullivan case, there will be code and data chunks for that data spread across many different computers. And so, least recently used means you have to track the access times. So you have to know if any of those chunks were accessed, not just a single one. So you now have to look at many different types of servers that your data might have been striped across and understand the full access patterns to all of them. So it can be a bit difficult to manage all the bookkeeping for that. However, it's more efficient than FIFO for almost all applications, and so we would get higher hit rates of our cache if we can do something like LRU. FIFO is easier to implement. It was the initial work that we did for this project. However, we've since moved to something more like LRU. Okay, so what does this look like? So a new file, so a new application is writing to the distributed file system here. So it's saying, here's, it's got something like the POSIX API to open a file. And the first question that the file system has to answer is, should I place this file on flash or on disk? If I place it on flash, how much flash is the user going to need, and for how long can I keep it in flash before I move it to disk? Now, if it goes to disk, it just goes directly to disk, and that's the end of it. And there's a couple of different things that can happen if it goes to flash. One thing that might happen is it might be deleted. So this line here from flash to disk, this is the expiration. So after, say the length of time is 1 day, after 1 day the data is copied from flash to disk. However, we have a lot of flexibility to do this. We can schedule this move at a time of lower I/O workload. So when the disk drives are idle, we can cause this migration. Some of the data will be deleted within that first day before it ever makes it to disk. So we've completely removed any need to touch the disk drives at all by hosting it in flash for a short period of time while it was used and deleted. And so this would be the right path. But how do we know, to answer that first question, that's sort of the key of the system, right? It's answering, do we store this data on flash or disk? And so this is the optimization that we do to make that determination. First, we gather workload statistics about the age of the bytes that are stored for different users. We look at sample RPC traces to look at the age of the data that is accessed. We use those two, these are stored as histograms typically, so we can have cumulative distribution functions. We compose them into a cacheability function, and I'll illustrate that on the next slide. And then we take these cacheability functions into a global optimization so that we can solve a linear program to optimally place data on flash so as to absorb the largest number of I/O operations per second. Because that's really what we're after, is taking I/O operations off of disk and moving them onto flash, because that gives us the best total cost of ownership for our provisioning choices about how much flash and disk we need to purchase. And the outputs of this optimization are, should an individual file have been placed on flash or disk, how much flash is needed, and how long it should live in flash before it's evicted to disk. Okay, I want to start here before I go into that slide. So ignore everything except the blue line on this slide to start with. I'll build this up. I wish I had a transition here instead of showing you all this complexity. But just look at the blue line. This is a CDF. It's a CDF of the bytes stored. And it's logarithmic with respect to the age. So this is a specific user that's storing 12 petabytes of data. 12 petabytes of data are stored. And if you look at the age, if you look at the median here, so if we go to like the median here, 6 petabytes of data, and we can read down 6 petabytes of data are less than 7 days old. So does this CDF clear to everybody? The blue, just the blue one. It's just a CDF with a log x-axis. And it's a absolute valued CDF. It's not really a CDF because it's not, I've got the real value here, 12 petabytes. But if this was a true CDF, this would be 1, and this would be the percentiles there. So I can, if this, the relative version of this would be the median, this is the 99th percentile, this is the first percentile. It's just a CDF, so it's just a histogram or CDF representation of a data set. And there's 2 data sets I'm looking at here. The blue line, which is the data stored on disk, and the red line, which is the data that's actually read from disk. So most of the data is accessed. Okay, so if you pick a point on this line, such as this one here. So this is 1 megabytes a second. This is the cumulative read rate of all the data. And if I look here, I can see the age of the hottest data. So most of the reads are going to data that's 1 day old or less. But most of the data stored is 7 days old or less. So there's a lot of colder data here that's not accessed as frequently. You can do a sort of the cacheability functions that we described are a way of composing these 2 CDFs to tell you how a percentage of, for a given amount of Flash, how many read operations can be absorbed if we store the youngest data in Flash? So if you pick 1 day, 1 day old would be about 2 petabytes of data. All of the data that's less than 1 day old is about 2 petabytes of data, but it's almost half of all the I/O operations. So it's a small fraction of the total data, but it's half of the total I/O load. And similarly, if we went further down here, we would get, we would get even a smaller portion of the data, but we'd still get a large amount of the I/O operations. And so that's what we're after. And these curves look different for different users, right? Some users have lots of hot data, some users have lots of cold data, and the optimal trade-off between those two users we can take as inputs to a linear program to solve. So we describe this composition of the two CDFs as a cacheability function that maps the amount of flash to the flash read rate. So it's mapping, and for this user, it's saying 2 petabytes of data, we can get half a megabyte a second of IOPS. And so here is that cacheability function showing what it looks like. So we go from, most of the read-ops are for very, very young data here, almost half. So you can see that there's sort of a knee in the curve here, and with just a small amount of flash, we can get most of that maps. But these shapes differ dramatically for different users. So how do we take those different inputs and optimize the allocation of data to them? Well, we have a number of goals when doing this. Our primary goal is to maximize the flash read operations rate to reduce the disk IOPS. So in this case, we can write this up sort of in an operations research syntax where we have an instance, workloads with cacheability functions and priority weight, and the total flash capacity that we have. Our task is to allocate flash to workloads to maximize the weighted flash read rate. And the solution method is simply linear programming. We can have some secondary goals with this, however. For example, we might want to bound the flash write rate. Flash devices have a limited number of program erase cycles that they can issue before they start to degrade. At Google, we look at the vendor specs and we run our own stress tests against the flash devices. We find that they typically last about 3 times longer than the vendor specs in our environment. So the vendor specifications are very conservative as to how many times you can program and erase them before they start to fail. Some of you may know more about this than me, or may have different experiences from different vendors. But there's SLC and MMC and many different types of flash devices. But in general, I would just say that the vendor write rates are very conservative. However, if we do know that we're starting to reach a limit, we can update the optimization to try to bound the flash write rate. So therefore, we might only decide that we want to insert things in flash if they're going to live and be used for a couple of days rather than just a couple of minutes. And leave the stuff that's only for a couple of minutes for RAM caching instead of flash. So we use a write probability for a workload. So what if we've determined that we have a workload that's a good candidate for flash, but it's larger than the amount of flash we can allocate to it. So for example, suppose we have a user that writes a bunch of data and then does a ton of reads to that data exactly 36 hours later. But over the course of 36 hours, they generate 2 petabytes of data, but we only have 1 petabyte of flash. So if we don't have a write probability, if we just sort of evict everything as we write it, then we wouldn't be able to cache any of that data, and with a very naive FIFO type system. So instead, we have a write probability where we can say, okay, well that's silly. Let's just give it a 50% chance of going into the flash cache, and that way, at least for 50% of the data, we store it long enough to get all those reads that we know are going to come to it 36 hours later. So one of the outputs of the optimization is a write probability. It's often 1, where we just insert everything to flash. But sometimes you get these cases where you have a large uptake of reads sometime down the future, and in order to take advantage of that, you need to set a write probability less than 1 to take advantage of that. The instance is workloads with cacheability functions and write rates. a bound on the flash write rate, and the total flash capacity. And in this case, it's a slight modification to the last linear program I described, where we allocate the flash to workloads to determine the write probability for each workload to maximize the flash read rate. I don't think I want to go through the math here, but it's pretty straightforward. This is just we're trying to maximize the phi is our cacheability function. We want to maximize the read rate with a bound on the write rate, W, some arbitrary bound, a bound on the total amount of flash, the xi's are the amount of flash we have for each user. So I guess we're summing over individual workloads, I here. Cacheability curve is per workload, the amount of flash is per workload, the write probability is per workload, and we want to maximize that. We can do a Lagrangian relaxation for the bound of the write rate. There's a convex approximation there. It turns out, basically, we can actually just use a greedy algorithm to solve this linear program, an O n log n, so we don't actually have to call out to a solver or do simplex or something because of some of the constraints that we have here. And so if you're interested in these parts, I can answer some questions about it, but it's probably better to look into the paper. But it's the main point is simply that because of the constraints we have, we're able to use a simple greedy algorithm for this, which is great, because it means that we can have this, we can do a lot of this online in the live production system without having all the complexity of trying to solve linear programs every time you want to write a new file. So how does this work in practice? Is it just too complicated and doesn't work, or is it useful? So this online flash allocation is used in Colossus, the main Google file system, for the last 18 months now in multiple data centers around the world. The optimization results are used by dozens of teams to influence future flash purchasing decisions. So it's not just used for online placement, but also for determining how much do I need to buy next year, how much flash do I need, how many disks do I need to purchase, and many teams use it for that as well. But we have a couple of questions we need to evaluate. How well does the past predict the future? I described how we use previous historical workload traces to determine which data is going to be hot and which data should be placed in flash, but that only works well as long as the past predicts the future. It doesn't work well if the workload changes dramatically. We want to compare it with alternative allocation methods. Maybe we could do something simple, right? Maybe we just give people flash proportional to the number of reads they're doing. Maybe we use a single global FIFO for all of the files, or maybe we use a single global LRU. We want to understand the impact on the bound of the flash write rate. Like, if we add a bound on the flash write rate, does it dramatically decrease the effectiveness of this system? Or are we still able to do a pretty good job and it's a negligible decrease? And then finally, we really want to understand the comparison between FIFO and LRU, at least at the time we did, because we knew LRU was slightly more expensive to implement. And so this was just a question, is it worthwhile? Should we spend 6 months modifying our systems, the way they do logging, the way we can collect distributed traces from our data centers in order to make a distributed LRU feasible? Is that worthwhile? A worthwhile way for a team of 6 engineers to spend 6 months? I think the answer was yes, it was. So this is where we came up with the name. So Janus is the god of beginnings and transitions, and so this is why we had this as our logo, looking back at past workloads and looking to the future about whether we should place data on flash or disk. And so the first thing we did was look at the flash hit rate during training and evaluation periods. So we can look here at how the training flash hit rates for different workloads and how well they work with the evaluation. It turns out that they were a pretty good fit, plus or minus 7 percentage points in most cases. So that was encouraging, but not that convincing. We wanted to look at how well over time, the predicted read rate to the data we placed on flash, how well did that match up with our prediction? So this is a single representative user where we predicted that we would be reading 32K ops per second, the data we placed on flash. Over the course of 2 days, it goes up and down, obviously, as the workload changes, but it was pretty good. Slightly, we didn't do quite as well as we wanted on average, but it was a pretty close match. And how does the optimized flash allocation compare with alternative allocation methods? The method I described is kind of complex. A simpler method would be to just give everybody some flash proportional to the amount of reads that they're doing. If somebody reads a lot, give them a lot of flash. If somebody reads a little bit, don't give them any flash. That's certainly a reasonable thing to compare against, at least. And so that's what we have here. We have proportional to data size. So this would be the simplest type of system you might have. Suppose you give everybody 1% flash of the bytes they store on disk. So if they store a petabyte on disk, you give them 1 terabyte of flash. That would be proportional to the data size. Then if we did that, what would the flash hit rate be globally to the cell? Well, it turns out that it would be up 14 or 15% for different data centers that we looked at. Cell in this context means data center. So one data center where there's a lot of different types. We chose 2 data centers which were very different. One had a lot of different weird workloads going on, and one was more stable. Okay, so then what if we had a single FIFO, where instead of having different FIFO queues for each user and optimizing between them, we just had a global FIFO queue for every byte that's read or written in the whole data center. In that case, we would get 19% hit rate in this data center and 42% in this data center. So it's starting to get pretty high over here. What if it's proportional to the read rate? So that sounds clearly better than proportional to the data size, because some users have lots of data, but they never read it. So you don't want to give a user that stores petabytes of old archival data a lot of flash. They're clearly not going to read it. So in this one, if you do it proportional to the read rate, how well do you do? Well, in this case, you get 26% or 64%. And finally, if we do our optimized method, where we're looking not just at how much reads they're doing, but crucially, how much reads to young data they're doing. This is one of the inputs to our optimization formulation, but also crucially, we're looking at the distribution of the age of their data as well, so that we can see if they're reading lots of young data, we give them more flash, whereas if they're reading some of the older data, which would not be as suitable for a flash, they're penalized in the optimization, they're not going to get as many. So we get another 10% increase by using this optimization method versus the proportional to read rate here. And that's just for these 2 data centers. Subsequently, we found a number of other examples where it was much greater win for us. So how does a bound in the write rate impact the flash hit rate and the time to live? If we are very concerned about the flash wearing out and we set a bound, then does that decrease those numbers from the last slide significantly, or do we still get most of that benefit? So imposing a bound in the write rate of 40% for some cells decreases the flash hit rate by only 3 to 5%. So this is a good finding for us. We only lost 3 to 5% of the effectiveness of our caching strategy by bounding the write rate significantly. And as I mentioned in practice, because we think the vendor write rates are extremely conservative, and in general we haven't done a great job of taxing the flash devices anywhere near their capabilities, we don't have much of a concern in this space. And even if we do start to have that concern, we only expect to lose 3 to 5% of the effectiveness of our system. So finally, what are the conclusions here? Flash has become cost-effective for cloud-scale distributed file systems if used selectively for some workloads. Our system, Janus, uses long-term workload characterization and then an optimization formulation to allocate flash for different workloads, maximizing the read rate and considering bounds in the write rate. Those 2 bullet points help us save many millions of dollars at Google, as you can imagine. Each of those warehouses, hundreds of thousands of disk drives. You can imagine the amount of flash devices you might need, or you can imagine how 8 terabyte or 10 terabyte disk drives that are coming in the future would be completely impractical for hotter data, but getting this right lets us save a lot of money. So it's been a very interesting, important project for us, for Google, and I think that there's many similar types of projects at other companies, but it's been fun to work on because it's all at this distributed file system level, right? So there's, we thought about this problem in a number of ways. One of the things we could have done would be to give the flash locally to each Linux node and have the Linux file system flash cache the data on flash itself, right? That's one thing we could have done. We could have modified ext2 or ext4, or written our own something in the buffer cache. We could have modified the Linux kernel and just made it locally cache data on flash. However, it's pretty clear that that approach has no chance of beating a higher level approach like this, because there's many reasons. But in a distributed file system, you have your data striped across different servers. Some of those are code bits, some of those are parity bits. All of the information about the higher level file system is above the level of a single node. And so the single node has no access to the information that it needs to understand how hot that data is going to be when it might be accessed again. You can push some of that down, but fundamentally it's a losing battle, because the distributed file system is a user space application running across all of these tasks. And the higher up the stack we go, the more information we have about user access patterns. So there's lots of great optimizations we can do at the Linux kernel level, but caching our data from our user space distributed file system is fundamentally going to be a flawed proposition to try to do at the node level. So we sort of killed projects working in that area to focus exclusively on doing this at the user space file system level distributed. So I think that's all that I have for this talk. I'm especially interested to hear from any students here about what you guys are talking about in your distributed systems class, and if there's any, I don't know if there's any questions or things we could talk about. We work on a number of different projects. There's a lot of things that I could have talked about, but I thought this project was a pretty interesting example because it has a lot of similarities to work that's gone on in Unix and on individual operating system levels for the last 20 years, but at the same time it's very modern and distributed, cloud-based, and it has a significant optimization component, which I like. So hopefully it's kind of an interesting survey of some of the type of distributed systems work that we do at Google. And yeah, I guess with that, are there any questions? Yes.
How much did it cost to calculate the linear program?
To calculate the what?
Linear program.
How much did it cost to calculate the linear program? So that's a good question. And we have occasional numerical stability bugs in our program. So we have our greedy algorithm. I think in a couple of times in the last few years we realized we weren't careful with our floating point math, and we got into an infinite loop or something where we were adding and trying to add up and solve this greedily. But in general, we can solve the instances in just seconds. So we can solve it, just seconds, because it's greedy. So we have a large number of users in a single cell, and we just solve it in less than 5 seconds. So we run this, but I didn't describe all the details here, but basically what we do is, my team is like a research group, and so the production team that runs our distributed file system, they didn't want us like writing a whole lot of code that went into the file system. So all of our stuff is kind of on the side. So we have this pipeline that we run that collects the data, it cleans it, it makes these graphs and visualizations so you can debug the system, and then it runs this linear program. And the linear program is just this continuously running server. It's just a C++ program, just a single instance that looks for new data, constructs the linear program, solves it, and then writes out its results somewhere. And so then the production file system, all they have to do is look for the results, they do a little bit of sanity checking, and if they're not there, they just do something, they use the last known good output they had. So the flash hit rate starts to degrade because it doesn't have the latest information, but it doesn't break anything. Users can still read and write their data. So my team maintains that optimization pipeline, and it's looping, and for each data center it just takes a few seconds to solve, but occasionally we have bugs.
I have 4 more questions.
Sure, great.
Great. If everyone has a question. So are you going to extend it to the multi-tier system, like there's a memory and PCI flash and SSD?
Yeah.
And the disk and the tapes, right?
Yes, that's a good question. It is Yeah, it's a very good question. There's so many levels of a thing like this at Google, and so our memory caching is mostly done at the node level. So we do have user space buffer caching for the files at the individual node levels. We are not coordinating the RAM caching in a distributed method across the different nodes currently. That is useful for a number of reasons, for both ways, right? The way we formulated all this work in this talk was moving data from disk drives to flash. But you could also ask the same question, which is, what RAM workloads can we move to flash, right? Which of our workloads are currently in RAM, and they're pretty hot, too hot for disk, but they're not too hot for flash, and we can just move them to flash. And that's a good question. It's a little bit harder because the logging and access patterns gets to be a bit harder, right? Because to do that, you really need to be logging your memory operations across like 100,000 servers or something, and so that just gets to be a crazy amount of data. But that's useful. People have asked us about that, but we do not have a handle on the raw data to do a good job at that right now, I would say.
And about the IO workload, in my understanding, you collected patterns for the IO workload without flash, right?
Yes.
And if we are using that Java system, then it's going to be changing.
Change, yes.
Yeah.
Yeah, that's a common problem we have. Basically, like with all dimensions in a distributed system, I think, when you free up more resources, the workload expands to use that resource. And so if we make reads and writes faster to flash, people start issuing more reads and writes. And similarly for other things. And so yeah, it's a good point. The workloads do change a little bit when people find they can do more IOPS, they redesign their systems. We don't have a great answer for that. It's part of this sort of general holistic approach of trying to slowly, the whole company and all the different teams are learning to use Flash better, and we're finding them modify their workloads slightly based on this. But yes, that's a good observation and something we kind of have to expect, but we can't quantify precisely. It's just too complex.
Would you tell me what is the attribute for the IO workload? Is that the read rate and the IOPS?
Yes, I was sloppy in my speaking a couple of occasions here. On most occasions, I basically meant things like read RPCs, which are on most cases going to be a random, sorry, that's not what I meant. Yes, what I was using was read RPCs that were not served by the node level buffer cache in user space. So those were, from the disk perspective, they were random operations, they were disk seeks. So I misspoke and said something about megabytes per second on one of the slides, but I almost certainly meant these read-ops per second, non-cached read-ops per second, because those are the ones, that's the closest proxy we have to actual disk seeks. I mean, we're not tracing the RPC all the way down to the kernel to understand if it really did see, and the firmware, because things can happen in the firmware as well to understand if it's a disk seek, but it's a pretty good proxy that it was not a hit in the buffer cache, so it was likely a disk seek.
I mean, my question was, for each application, you will have some kind of input as what the application is requiring as a workload, right? And what is the attribute for that? So is it only the IOPS, so that if there is I don't know, Gmail application, and the attribute would be some 100 IOPS?
It's two attributes for the cacheability function. It's the read rate by age of data stored and the bytes stored by age of data stored. It's those two CDFs, or two histograms, the red and the blue ones. So those are absolutely the attributes that we use. And so this is much better as a transition in some of my other slides where I explain it and I show one plot. This is a lot to absorb all at once. But basically, these come from histograms. If we have 100,000 servers, so we have a big MapReduce job that with thousands of workers, it looks at every file on every one of those servers, and it looks at the age of that data, and like the last time it was accessed, it bins it into a histogram, which is bucketed logarithmically by age. And so we can plot, I can plot that as a histogram, but it's easier to see as a CDF here, so I'm plotting the CDF versions here. And those are the two inputs. Those are the attributes of the workload, are the age of data stored and age of data read. And in almost every case, the red line is over here, meaning that the data is read, the younger data is more likely to be read than just the data stored on disk. And so that's the key. So we started with this. So if I, in other versions of this talk, I basically start with this slide because 2 or 3 years ago we generated this plot, and this led to the feature. We recognized that this was a common pattern of people storing data on the Google file system where they would read only their youngest data, and the old data was seldom read. And the degree to which they differed varies a lot between users, so that points to the fact that we should find the users where there's a significant difference, where most of their data is to reads or to really young data, but maybe they're also storing some really old data, they just never access it. Those are the great candidates for flash caching. And so, yeah, these two attributes, we combine them into a single cacheability function, which is plotted here. It's a parametric curve of this and this. Like this is the x-axis and this is the y-axis to get you this.
Okay, so that graph in the previous, yeah, I'm sometimes curious about the performance of the cumulative read rate. Is that 1.0 megabyte per second? Isn't it too low?
What? So it's millions. So I guess this is a million reads a second, not a megabyte a second. It's a million reads a second. Yeah, this is the one I was thinking of where I misspoke actually. So I said megabyte a second, but I meant this is 1 million reads a second to 12 petabytes of data.
Yeah, makes sense.
So that makes more sense, right? That's yeah, 1 million reads a second, 200,000 reads a second here for 4 petabytes of data.
Thank you.
Sure. Any other questions about Google distributed file systems, Colossus, Google data centers, or I don't know how Google uses open source operating systems at the base levels?
How many folks worked for this project?
How many people
Yes.
worked on this? So the my team. There was about 5 people on my team doing this. That includes a full-time statistician, a full-time mathematician, doing the Lagrangian. Does anybody know what a Lagrangian approximation is? I don't really know what it is. I'm asking. And so I don't have an optimization background, but we have a couple people that did OR PhDs, and so they convinced me that this greedy thing works. And in evaluation, it does work. But so we have some specialized people like that working on this. Maybe 3 software engineers on my team, a statistician, an optimization person. And that's on our researchy side. So we were writing reports and giving talks and trying to convince people to do this. But we didn't write a whole lot of production software. The production Google file system team is spread across in New York and Mountain View offices. And probably just like 2 people on that team worked on this feature. The rest of them were working on other things. And then there's like our node level chunk server system that runs on individual Linux servers. And maybe just a fraction of one person's time on that team was aware of what we were doing. We were coordinating with them on some logging issues. We had to talk with them about how to get LRU working at scale across hundreds of thousands of machines, how to make sure we accounted for buffer cache hits and misses as a proxy for what's a real disk IOP and what's going to just be served by the RAM cache, and so it doesn't matter if it goes back to disk. So on the order of approximately 8 people worked for a few months, for like 6 months or so on this project.
Right. And one last question. If you know, please tell me, how much money Google can save using this new file system or software?
That is a good question. Definitely in the many millions of dollars. I mean, I guess I can't say much about scale of purchases of disk and flash that is large. It's very large. And so I think if you just take 1% improvement to those very large numbers, it would pay for everybody's team times 100 for 10 years or something. So that's one of the things, that's actually a good point about why I love what I do in my group. My group is storage analytics, and we do things like this. This is one example, but in general we use math and statistics to look closely at the way our software works and find ways to improve the system. And other things we're trying to do is like, what if we just saved 1% of all I/O operations globally in the fleet? We have all these disk drives, and what if 1%, and sometimes we buy disk drives solely because the disk time fraction is too high in the whole data center. The spindles are always busy randomly seeking, so we have to buy more disks. And if we can reduce that by 1%, we save an enormous amount of resources. And so we have, if you haven't seen them, let me see, do I have them as a backup slide? Jeff Dean has these rules of thumb. Okay, well, one thing that it's not in the slides, but I highly recommend you look at Jeff Dean's rules of thumb for the equivalence of different operations. And this guides a lot of, I think, our internal thinking about resource trade-offs. So, for example, what's the cost of sending 1 megabyte of data across the Pacific Ocean? Or what's the cost of keeping that same megabyte of data on a disk for 6 months of time? Or reading from cache, or reading from flash. And so there's a slide deck out there on the web from Jeff Dean, which highlights the equivalencies of many of these operations. And so one of the ones, for example, I think that we've talked about is transoceanic copies. It's just as expensive to copy the data once across the ocean as it is to keep it spinning on a disk drive for 6 months. So if you have to copy across the ocean and you have free disk space, you may as well just cache it locally for 6 months or more to make sure you don't have to ever copy that data again. So that would be the type of thinking and trade-offs we use to make sure we're minimizing our total cost. But I can't get into more specifics about the number of disks we have.
What is the name of the rule again?
Of the what?
Rule or the
rules of thumb. So Jeff Dean is. I don't think I have Wi-Fi. Can I get on Wi-Fi here?
No. Jeff Dean.
So Jeff Dean is one of our principal engineers. Jeff Dean.
He's the creator of the GFS.
Yeah, and not producer. Yeah, he's on all and Bigtable. He's on all of our main papers. And he looked for rules of thumb, and he's got these really great rules of thumb because they're all normalized. So he can just say like, he doesn't have to disclose any details about Google's fleet, but they come from observations of a really large number of computers and disk drives and failure rates and things like that. So I highly recommend taking a look at that. Any other questions?
Do you have any updates after using XADC, or did you have any question at the conference?
Yeah, that's a good question. I guess our main action item after using XATC was like, why are we using FIFO? LRU is clearly better. So we spent 6 months rolling out a new sampled logging infrastructure, which is actually pretty interesting. So we have, normally with RPC sampling in a large-scale distributed system like this, you have an RPC library that sends requests over TCP to other nodes, and you just have some sampling probability or something, and whenever you run out of space, you downsample further. And we have some of these systems at Google. Ours is called Dapper. Twitter has Zipper or something similar type of system, and there's others out there. Faye, I think, is another from Microsoft Research. But those are insufficient because you can't do LRU with something like that. You can't do LRU with something where you are just uniformly sampling RPCs. Instead, you have to uniformly sample entities, such as files, and for a subset of those files you select, you have to log 100%, you have to log everything. So that way you get the reads and all the writes to that subset of the files. So what we did was we implemented a reservoir sampling library in our node-level file system to keep track of a collection of the RPCs that went to that node, and to keep very careful statistics about any downsampling. So this is just logging, so if the computer starts to get overloaded, we have to drop samples. We can't degrade performance just for the sake of logging. However, crucially, we put tight statistical bounds on any errors that are introduced because of this. If we drop samples, we record exactly how many we drop, and we randomly pick which ones to drop in a way that doesn't bias the results. And then we also have something at the higher level storage systems where they can set a bit to do our entity-based samples, where they can say, okay, for this entity, sample 100%, no matter which server among the 100,000 that it goes to, sample everything. And so that allows us to do distributed LRU in a reasonable way. We might write up a paper for Lisa or something about that. It's a little more narrow, it's very logging focused. I'm not sure how applicable it is outside of Google, but it was an interesting project, and that was the main work we did after this project. Other things, I guess there's a couple of other things I can say. Bigtable is built on top of Colossus, and Bigtable is like HBase for people familiar with the Hadoop ecosystem. And so for the same argument, I say that it doesn't make any sense to do your caching at the Linux file system level if you have a distributed system on top of it. By the same token, if most of your data going to Colossus is from Bigtable, you'd have a lot more information about specifically which rows and columns and keys are being accessed at the Bigtable level directly, rather than at the Colossus level, which is just a file store on the back end for Bigtable. So there's been a lot of work at a specific caching systems for things like Bigtable. It doesn't replace this because many systems use Colossus directly, they don't go through Bigtable, and Bigtable still benefits from this, but it's something that most Bigtable users would probably be better suited to use this more Bigtable specific offering that another team has developed. So that would be some other big area of work that's come up, I guess. I have some notebooks, actually, so swag from Google. I can pass out for people that want them. I'm sorry, I don't quite have enough. I'm going to put them here. I'm going to give them first to people who ask questions. And then I'll put the remainder over here. Yeah, the Google office in Roppongi is very nice. I was last here in 2007 for Asia BSDCon, I think, and I also visited the office when it was in Shibuya. But the view is amazing. It's a wonderful office. If you're looking for a job, I would highly recommend talking to the Google recruiters. Many different types of jobs. I don't think they do distributed storage here, though. They do a lot of mobile application stuff, and some web search and advertising, lots of interesting projects, but they don't do file system level work at Google Tokyo as far as I know. Thank you for coming. Thank you for listening.
オンエアは5時過ぎぐらいまでやってますので、もし個人的に質問したいこととありましたらぜひで5時過ぎから国際会議の駅前の飲み屋を取っていまして、そこに移動してもしお時間あるようでしたらお願いいただきます。どうも今日はありがとうございました。